Hey everyone, and welcome to this explainer. Today we're diving into the pretty fascinating world of sensors. You can kind of think of sensors as our mechanical senses in what is honestly an incredibly noisy and chaotic world. They're these absolutely crucial translators, right? Taking physical reality, stuff like pressure, light, temperature, and converting it into the digital data that runs, well, our entire modern lives. But how exactly do they pull that off? And maybe more importantly, how do we actually know if they're telling us the truth? So that brings us to a really simple question, but one that hooks right into the very heart of engineering. Is any measurement ever truly perfect? The short answer? Absolutely not. No way. Absolute perfection in measurement is just a complete illusion. Every single time we measure something out there in the real world, there's a tiny bit of deception involved. Our job isn't to somehow find a perfect measurement, but rather to figure out exactly how much our sensors might be, lying to us.
Okay, let's dive into this. Here is our roadmap for today. First, we'll look at the flaw in every measurement. Then we'll get into signal, noise, and statistics. After that, we'll quantify doubt with measurement uncertainty, tackle some real-world sensor math, and finally, we will classify the sensor world. Let's get to it.
Section 1. The flaw in every measurement.
Now, if we're going to trust our data, we first have to establish exactly why our measurements are constantly deviating from the absolute truth. And it basically boils down to two main categories of error. Over on the left, we've got gross errors. These are the human mistakes. A technician reading a dial wrong, accidentally dropping a wrench, or maybe a piece of equipment just completely malfunctioning. If you have a gross error, you fix the machine, or honestly, you might just need to retrain your technician. But on the right side, we have random errors. These are the unavoidable small fluctuations in the universe. We're talking tiny temperature shifts, micro vibrations. These are literal forces of nature. We can't go firing someone over random errors. Instead, we have to tame them using mathematics.
Section 2. Signal, noise, and statistics.
So, since we know we can't just escape those random errors, let's introduce the mathematical detective tools that engineers rely on to filter out the noise and find the real story. The very first tool in our kit is the SNR, or signal-to-noise ratio. It's actually remarkably elegant. You simply take the strength of the true signal you're trying to measure, that's your mean, or your average, and you divide it by the random noise, which is represented by the standard deviation of your fluctuations. It literally calculates the strength of our desired truth right against the background chaos.
Now, depending on how that calculation shakes out, you're going to end up with either a high SNR or a low SNR. With a high SNR, your signal is crystal clear. The random error is just a tiny, insignificant blip compared to the actual thing you're measuring. But a low SNR, that means your signal is super noisy. And here is where it gets really critical. If your SNR drops to less than 1, it means the noise is literally louder than your signal. Without some heavy mathematical filtering, your sensor data at that point is essentially useless.
Okay, another great tool we use is calculating residuals. A residual is just the difference between one single measurement and your overall average. It tells you the exact amplitude of the noise at any given split second. So if you see a really large residual, that immediately points to an outlier, like a big spike in your data. But if your residuals are consistently small, well, that means your sensor is reliably stable. In fact, in a perfectly stable system, if you were to add all your residuals, they should completely cancel each other out and just equal 0.
And this brilliantly illustrates our next core concept, standard deviation. When we want to really quantify that precision, we use standard deviation to tell us exactly how much our sensor values scatter away from our best average guess. A high standard deviation means your measurements look kind of like a blurry cloud. It's noisy, it's unreliable. But a low standard deviation means your measurements form a really tight cluster. That tells us the sensor is highly repeatable.
Section 3. Quantifying doubt. Measurement uncertainty. We're going to shift gears a little bit now. We've gone from just finding our errors to formally accepting and mathematically reporting our doubt. You see, in professional engineering and science, you almost never state a measurement as an absolute, rock-solid fact. An engineer is never going to write down that a reading is exactly 5 volts. Instead, they'll report that measured value with a plus or minus uncertainty window, so something like 5 volts plus or minus 0.1 volts. Uncertainty isn't a mistake, right? It's the specifically quantified range where we confidently expect the true value to live.
To figure out what that window actually is, we look at two distinct types of uncertainty. Type A uncertainty comes from your own, live, hands-on measurements. It's derived directly from the random error, the actual noise and fluctuations you observe while you're testing, so it represents the human or environmental repeatability of your test. Type B uncertainty, on the other hand, doesn't come from your tests at all. It comes straight from the manufacturer's specifications and calibration certificates. It represents systematic error, which is basically the physical, built-in limits of the hardware itself.
Naturally, out in the real world, you're dealing with both of these at the exact same time. So we use what's called the combined standard uncertainty formula. This lets us blend our Type A live test doubt and our Type B hardware doubt into one single ultimate metric of confidence for our final report.
Section 4. Real-world sensor math.
Let's move to and see how this builds in an actual scenario. I want you to put on your technician's hard hat for a minute. Imagine you've got a pressure sensor and it's measuring a constant tank pressure that we know for a fact is exactly 50 psi. Over 5 trials, our sensor reads 52.1, 52.3, 51.9, 52.2, and 52.0 psi. So first, we calculate the mean, which averages out to 52.1 psi. But wait, notice that our average is higher than the true 50 psi tank. That difference right there, that's our systematic error or our bias. Finally, we look at how those readings are bouncing around that average to find our random error spread.
So how do we actually fix this? Well, our math is telling us we have a constant offset, a systematic error of plus 2.1 psi. We also have a random error range that's fluctuating by plus or minus 0.2 psi right around our mean. Now, we can't eliminate that random fluctuation easily, it's just part of the system, but we can completely neutralize the systematic error. We do that simply by either recalibrating the sensor itself or just programming a straightforward minus 2.1 psi mathematical correction factor into our software.
Let's try one more, this time with a strain gauge. This is a device you'd bond to a steel beam to measure how much it's bending. Now, the manufacturer's datasheet tells us there's a nominal gauge factor with a built-in systematic tolerance of plus or minus 1%. So, if our instrument gives us a reading of 1,000 microstrain, that tiny 1% manufacturer tolerance immediately causes a built-in systematic error of 10 microstrain.
Furthermore, because strain is inversely proportional to that gauge factor, if the actual physical gauge factor happens to be higher than the nominal setting we originally programmed in, our instrument is going to overestimate the physical strain. The really crucial takeaway here is that knowing your sensor's underlying math is literally the only thing preventing you from acting on false inflated data. Think about it. Without this math, you could be shutting down an entire factory line for a bent steel beam that is actually perfectly fine.
Section 5. Classifying the sensor world.
Okay, we've talked a lot about the abstract math, but let's zoom out and look at the incredible physical hardware that actually gathers all this data. There is just a staggering variety of ways these devices feel the world around them. For example, photoelectric sensors shoot out infrared or laser light to detect objects. Inductive sensors? They generate invisible electromagnetic fields specifically to hunt for metal. Capacitive sensors can detect almost anything by sensing subtle changes in electrical capacitance. Ultrasonic sensors listen to bouncing sound waves to measure distance and levels. And piezoelectric sensors physically convert pressure and heavy vibrations directly into electrical voltage. It's really amazing stuff.
We also classify these sensors by how they get their power and how they actually remember their place in space. Active sensors are self-generating. The physical effect itself creates the electricity. Passive sensors, though, need an external power supply pushed into them just to wake them up. When we talk about tracking movement, an absolute sensor always knows its exact position against a fixed reference point, even if you unplug the power. But an incremental sensor only tracks movement relative to its last known point. So if an incremental sensor loses power, it completely forgets where it is and has to start all over again.
Now, what's really interesting about this slide is seeing it all come together. Take a look at these rugged physical devices. You've got a heavy-duty pressure gauge mounted right on a pipe, and a highly precise photoelectric laser sensor bolted to a rail. All that deep statistical math we just talked about, the standard deviations, the uncertainty calculations, the signal-to-noise ratios, ultimately, all of that theory lives inside these very real physical objects that are out there running our modern world.
Which really leaves us with a fascinating reality to ponder. We rely on smart thermostats, automated cars, and massive, complex industrial grids every single day of our lives. But knowing that every single sensor out there carries hidden uncertainties, built-in systematic errors, and is constantly fighting against the random background noise of the universe, how much do you truly trust the automated readings that run your daily life? The next time you look at a digital gauge, I hope you remember the beautiful, hidden math working overtime just to give you that one simple number. Thanks for joining me on this explainer, and keep questioning the data.